Welcome to an introduction to the strategy for finding constrained extrema known as Lagrange multipliers. So our objective here is to learn about how to use the method of Lagrange multipliers to help us solve optimization problems where there is a constraint on the problem. Let's start with a motivation for the method. So suppose we have a profit model for a company and we want to maximize the profit for that company. If the profit model has inputs of X and Y, so X represents the number of widgets sold per month measured in thousands, and Y is the number of hours advertising or advertising hours per month. So we have a function, profit, P of X and Y, equal to 48x plus 96y minus x squared minus 2xy minus 9y squared. Now, our profit function, or the output of that function, is measured in thousands of dollars. So in real life, when you're doing manufacturing, there are always constraints on the manufacturing process. So we're just going to capture some budgetary restraints or constraints that are modeled by this equation g of x and y equal to 20x plus 4y equal to 216. So our goal is to find values of x and y that make this profit function maximum. So we want to find x and y, or the number of widgets sold per month and the number of hours of advertising per month, that will produce maximum profit. And we also want to determine what is that maximum profit. Well, this problem can be solved using the concept called Lagrange multipliers. Lagrange multipliers is a process by which we solve the equation gradient of P equals lambda times gradient of G. So solving this system of equations in terms of lambda will typically help us identify those values of x and y that maximize our profit. So now let's go ahead and look at some visualizations. So the goal here is to determine the extrema of the surface of a function, so a z equals f of x and y, subject to some type of constraint, g of x and y equal to k. Now, in that previous motivating example, our f of x and y was profit, so the profit function, if you were to graph it, creates a surface. We want to find the maximum of that profit function subject to, and our constraints were an equation that captured budgetary restraints. So we're going to look at some animations here and to help us understand or get a glimpse into is probably a better description of this method of Lagrange multipliers. So let's take a look at this animation. We're going to start with the creation of our surface. Here is our surface, our f of x and y, that we're seeking the extrema for. And now we're going to impose our constraint, our g of x and y. And here is our constraint function. Notice how it passes through our surface, f of x and y. And so as we're looking at this, you'll notice that there is a circle and ellipse. It's difficult to tell which it is, where the surface intersects our constraint intersects our surface that we're interested in. But as you'll notice, along this intersection here, we have a maximum value and we have a minimum value. Now, looking at this again, slightly different interpretation. There's our surface. Here is where we have that region we were interested in, where our constraint intersected our surface. Now look, we're looking down the z-axis, and what we see here are the level curves of our function of x and y. And now we're going to superimpose that region from our constraint. And you'll notice that as we do so, that the maximum and minimum values for our surface, for our function f of x and y, subject to this constraint, occur along level curves. The minimum is along this level curve 1, and the maximum is along this level curve 4. So let's take a brief look at why this technique of Lagrange multipliers works. So we're going to start by introducing our constraint. This green disk represents that constraint. And now we have a series of level curves introduced onto our XY coordinate axes. Notice we've got 17, 16, 15, and so forth, all the way down here to 4. And notice how some of these level curves align perfectly with the boundary of our constraint function. Now, what we have here are two gradients. One is the gradient of the function, and the other is the gradient of the constraint. And recall that that equation we saw earlier was gradient of f of x and y equals lambda times gradient of g of x and y. That means that the two gradients are scalar multiples of each other. And so if the two gradient vectors are scalar multiples of each other, then they point in the same direction, that they are parallel. Now notice down here at our other point of tangency, where the level curve is tangent to the constraint, we see the purple vector, which is the gradient of f. And now we see the gradient vector for our constraint function, the gradient of g. And notice that in both cases, that the gradient of f is equal to the gradient lambda times the gradient of g. Now, why is this significant? Recall properties of gradients. Gradients always point in the direction of greatest increase. Their opposite points in the direction of greatest decrease. So those can help us identify maximums and minimums. So now that we've had a glimpse of why we might solve an equation like gradient of f equal to lambda times gradient of g to find extrema for a function, let's return to our example here, and we'll outline the process or the strategy for solving a problem using Lagrange multipliers. Notice that we have the function we're trying to maximize here, this p function, and we have our constraint function here. So we've actually done the first step in solving a problem like this using Lagrange multipliers. We have to know what our objective function is and our constraint function. We didn't actually call this function, our profit function, the objective function, but that is its name. And we identified that we are indeed looking for a maximum value. So here's our objective function, and here is our constraint. So next we need to set up a system of equations that we can solve to find the location of our absolute So next we need to set up a system of equations to solve using this. Next, we need to set up a system of equations using the gradient of f equals lambda times the gradient of g. Notice that we are going to use coordinates x naught, y naught, and we're going to solve for those unknown coordinate values for which this statement is true. So let's go ahead and we'll start by finding first, in our case, we want the gradient of p. So we'll find that first. In the gradient of p, the first component is going to be the partial with respect to x. So for my first term, that's going to be a 48. Plus, the partial with respect to x of the second term is 0, so I'm not going to write that. The partial with respect to x of our third term is 2x, so minus 2x. The partial with respect to x of our fourth term is going to be minus 2y. And then the partial with respect to x of our fifth term is 0. So there's our first component, our x component, our partial of our function p with respect to x. And now we're going to do similar. We're going to find the partial of p with respect to y. And in my first term, that's going to be 0. The partial with respect to y of my second term is a 96. Partial with respect to y of the third term is a 0. Partial with respect to y of our fourth term is going to be a minus 2x. And then the partial with respect to y of our last term is going to give me an 18y. Next, I need the gradient, of g. And so in the x component, we're going to have the partial of g with respect to x. So that's going to be 20. And in our y component, we're going to have the partial of g with respect to y. So that's 4. So there's our two gradients. Now we want to set up this system. So we want the gradient of p at the point x naught, y naught is equal to lambda times the gradient of g at x naught, y naught. Well, so that gives us, substituting x naught, y naught into p, the gradient of p, I get 48 minus 2 times x naught minus 2 times y naught, comma, 96 minus 2 times x naught minus 18 times y naught. So that's our gradient of p at x naught, y naught equals lambda times, and now I want the gradient of g at x naught, y naught. Notice that the gradient of g consists of constants, so there's no place for me to substitute in an x naught or a y naught. So when I write this equation, then the gradient of g piece is just going to be the vector 24. So we'll just quickly distribute this lambda throughout our vector so that on the right-hand side, we've got a vector with 20 lambda, comma, 4 lambda. So we have our two equations that we got from the gradient of f equals lambda times the gradient of g, or in our case, the gradient of p equals lambda times the gradient of g. Now we're going to add to this system of equations an additional equation, and that's based on our constraint function. We need this additional equation that our constraint function g of x naught y naught is equal to 0. Now recall that the constraint function we were given was 20x plus 4y equals 216. So we're going to take this equation, we're going to rewrite it and set it equal to 0. So we'll have 20x plus 4y minus 216 equals 0. And then this expression on the left-hand side of the equal sign becomes we end up using for our g of x and y in our system of equations. So instead of rewriting our constraint function with the right-hand side equal to 216, we need to have that right-hand side equal to 0. So the third equation here becomes 20x naught plus 4y naught, and then that is a negative 216. I'm just lining up like terms here. That is equal to 0. So this is the system of equations that we need to solve. And so let's go ahead and take a look at how we might do that. Now, one strategy that we sometimes use would be to take this first equation and solve for lambda, take this second equation, solve for lambda, and then set the two equal to each other. So if I were to take this first equation and solve for lambda, I would end up dividing by 20. So I'm going to actually write lambda equals over here on the left-hand side, just so we can keep track of what we're solving for. So I would have 48 minus 2x naught minus 2y naught all over 20. And that's solving the first equation for lambda. Now if I do the same for the second equation, I would have to divide both sides of the equation by 4. So if I do that, I get 96 minus 2x naught minus 18y naught, all divided by 4. And so what I can do then is focus on solving this proportion or this set of equations. I think the easiest thing to do to solve this set of equations would be to multiply both sides of these equations by 4. I'm sorry, by 20. If I multiply both sides of the equation by 20, the denominators all divide out, and I'm no longer dealing with fractions. I'm dealing with integers, which are much easier to work with. So on the left-hand side, I now have 48 minus 2x naught minus 2y naught. And on the right-hand side, I've got that expression in the numerator times 5. So I'm just going to write it this way. I'm going to write this as 96 times 5 minus, and then 2 times 5 is 10. That's easy enough. 10x naught. And then 5 times 18 is 50 plus 40, so that's minus 90 y naught. Now notice we have one equation, but it has two variables. But if I go back up and I look at what I started with, I had 3 equations and two variables. So notice that I've used the first equation and the second equation in my system to generate this new equation that I have. I have not yet used my constraint And that constraint contains a relationship between x naught and y naught. So what we're going to do is we're going to solve this new equation we created. We're going to solve that for one of the variables. I'm going to choose x naught and use that in our constraint equation. So let's see how that would work. I'm going to add 10x naught to both sides of the equation because I'm solving for x naught. I'm going to subtract 48 from both sides of the equation, and I'm going to add 2y naught to both sides of my equation. So what ends up happening is these 48s sum to 0, and these plus and minus 2y naughts, they sum to 0 as well. So I'm left with a positive 8x naught on the left-hand side of my equation. And to make simplifying a little bit easier, I'm going to keep the right-hand side as 96 times 5 minus 48. Our negative 10x naught and our positive 10x naught, that will sum to 0. And negative 90y naught plus gives us a minus 88y naught. Now, in this form, it's straightforward to divide by 8. So let's go ahead and divide everything by 8. 8 into 8 goes once. 8 into 96 goes 12 times. 8 into 48 goes 6 times. And 8 into 88 goes 11 times. So what we have now is that x naught is equal to 60 minus 6 minus 11y naught, or x naught is equal to 54 minus 11y naught. Now, we're going to use that in our constraint function that we haven't used yet. That's going to help us to determine the value of y naught because we're going to replace x naught in that equation. So we've got negative 216 plus 20 times, now our x naught is 54 minus 11y naught plus 4y naught equals 0. Going to add 216 to both sides of the equation, so plus 216 plus 216. I'm going to distribute my 20 through those parentheses, and so I end up with 1080 is equal to, or I'm sorry, that's 1080 is minus 220y naught plus 4y naught equals 216. Combining my two y naught terms, I have 1080 minus 216 times y naught equals 216. Now, given that I've got 216 in two places, I'm hopeful that 1080 is divisible by 216, and it does turn out that it is. So I can divide everything by 216 like that. And let's see, 216 into 1080 goes 5 times, and then 216 into itself goes once. So what we have is 5 minus y naught equals 1. So let's subtract 1 from both sides of the equation and add y naught to both sides, and we find out that y naught is equal to 4. Once we know that y naught is equal to 4, we can come back and use what we know about the relationship between x naught and y naught, and we can find that x naught is 54 minus 11 times 4, because y0 was 4, and that ends up giving us that x0 is equal to 10. Okay, so we're almost done. These are the values of x and y that produce a maximum profit. So let's go ahead and finish answering that. So we found our x and y values of x equal to 10 and y equal to 4. And so we can then substitute those values into our profit function. When we do that, we end up with an output of 544. The question is, 544 what? Well, our maximum profit is $540,000, and it is earned when 10,000 widgets are sold per month and there are 4 hours of advertising. Notice that it was important to attach the units to each of these quantities in stating our answer. I hope you find this helpful.